Okay, let's jump right into this ultimate explainer on the ESP32 microcontroller. We're going to bridge that gap between high-level hardware theory and actual practical embedded coding. Whether you've just tinkered with a few Arduino sketches or you're already architecting a robust, low-power sensor network, truly understanding what's happening under the hood of this remarkable chip is a total game changer.
So, here's our roadmap for today. We'll be taking a bottom-up tour, covering the ESP32 memory and architecture, routing with the GPIO matrix, touch sensors and ADCs, managing peripheral interrupts, and finally, we'll wrap up with sleep modes and the ULP.
All right, Section 1, ESP32 Memory and Architecture.
To kick things off, let's look at why this chip really is the gold standard for IoT projects right now. The ESP32 isn't just a basic microcontroller. It's a highly versatile system on a chip. It is packed with raw, dual-core processing power. It can handle incredibly heavy communication stacks, like TCP/IP and TLS, without even breaking a sweat. Plus, it bundles Wi-Fi, Bluetooth Classic, and Bluetooth Low Energy all into one single integrated package.
Now, the memory management unit efficiently organizes the internal SRAM by structuring it into independent 32-kilobyte banks. Because of this clever hardware design, the CPU and the direct memory access, or DMA, channels can actually access data at the exact same time. There are zero hardware bottlenecks, as long as they're looking at different memory banks. That is an absolute massive boost for any of your data-heavy tasks. Moving right along to Section 2, routing with the GPIO matrix. Stepping out from the core, the GPIO matrix essentially acts like this massive, programmable switchboard. With a lot of older microcontrollers, specific pins are hardwired to specific functions. You're basically stuck with what you get. But here, the matrix lets you route 162 internal peripheral inputs to almost any of the 34 physical pins. It just gives you unbelievable flexibility when you're designing custom-printed circuit boards.
And while the internal wiring might sound super complex, configuring a simple digital output at the hardware level really just boils down to 3 precise register steps. You clear the output configuration, you enable the data driver to turn it on, and then you just tell the I/O mux to select the GPIO matrix. It's a really logical progression from a software command right down to a physical hardware state.
The really crucial takeaway here is how all of this dense hardware routing perfectly translates into those beautifully simple Arduino functions you're probably already using to control things like LEDs. When you call a basic digital write to make a pin go high and then low, you're actually abstracting away all those matrix and mux register commands we just talked about. The chip is doing all that heavy lifting behind the scenes for you.
All right, Section 3, Touch Sensors and ADCs.
Next up, let's give our microcontroller some actual senses. You really don't need a complex external module to detect human touch anymore. There's a dedicated, hardware-implemented finite-state machine that controls the 10 capacitive touch pins on the ESP32. This FSM is constantly autonomously monitoring for capacitance variations on the physical pads, so the main CPU doesn't have to constantly babysit it.
The setup for this is surprisingly straightforward. When your finger touches an external electrode, honestly, it could be as simple as a looped wire, that change in capacitance triggers the hardware loop to flag a valid touch event. And get this, it can even use that event to wake the entire system up from a deep sleep.
In practice, if you use a simple touch read command on a designated pin, say GPIO 4, it pulls an analog value. And that value drastically drops the exact moment you make physical contact, like dropping from around 57 down to 17. It's just an incredibly effective way to create custom hardware interfaces, hidden buttons, or even interactive displays without needing any moving mechanical parts. Now, for reading other more complex analog signals from standard sensors, the ESP32 relies on 5 specialized controllers. These manage its dual 12-bit SAR ADCs across 18 different analog pads. This setup gives you really nice high-resolution readings ranging from 0 to 4095 for pretty much any environmental input you throw at it.
Moving on to Section 4, Managing Peripheral Interrupts. Now that our chip can sense the outside world, we need to teach it some reflexes. The interrupt matrix basically serves as the traffic cop of the ESP32. It independently allocates peripheral interrupt sources to the 2 processors to keep your system highly responsive. So, if a sensor suddenly triggers, the matrix ensures the right CPU drops whatever it's doing to handle that alert immediately.
But you might be wondering, how does this actually work when the chip generates 71 different hardware alerts across the board, but only has 26 interrupt slots available per CPU? Well, that's exactly why this matrix maps them so flexibly. It routes the most critical alerts from your peripherals directly to the available CPU interrupts, making absolutely sure nothing gets bottlenecked.
To configure or troubleshoot these reflexes, embedded developers basically map their peripheral source to a specific CPU interrupt number, and then they query the specific status register to verify exactly what triggered the event. It gives you this amazing microscopic control over exactly how your hardware prioritizes its tasks.
Finally, Section 5, Sleep Modes and ULP.
Let's talk about endurance, which is absolutely crucial for IoT. This data paints an incredible picture of power efficiency. Dropping the chip into deep sleep reduces current consumption from a somewhat hungry 800 microamps down to a mere 6.5 microamps. And the best part? You still retain your crucial RTC or real-time clock memory, so your device doesn't wake up with complete amnesia. Understanding the power control architecture shows exactly how this is achieved. The power controller isolates different domains. This allows you to entirely power down the power-hungry digital core, which includes both the main CPUs and the wireless radios, while safely keeping the low-power analog RTC peripherals and slow memory awake and functioning.
During these deep slumbers, the ultra-low power, or ULP, coprocessor essentially takes the wheel. It runs on a highly efficient 8 MHz clock to independently monitor sensors, like the touchpads or the ADCs we discussed earlier. It'll just quietly do its thing, and it only wakes up the main, power-hungry system when it detects a critical threshold has actually been reached.
So having mastered the hidden architecture of the ESP32, from cleverly multiplexing your GPIO pins to sleeping ultra-efficiently with the ULP, the only real question left is, what smarter, more power-efficient hardware project are you going to build next? Thanks so much for joining me for this explainer, and happy building.